Recording is rolling. It is Wednesday, December 6th. I have a rotational inertia lab lined up for you guys today. You guys have paper in front of you. I'll help you guys make this table and collect the data. We're going to do a version of this lab where I have this whole contraption in front of me. You guys see this whole pipe system in front of me right here, right? We're gonna do a guided lab, right? So I'll do the setup. I'll have you guys tell me times. You guys have stopwatches on your desk, right? I'll guide you guys through step by step, right? There's different advantages to doing different labs different ways. The advantage of doing it this way is that, well, I can tell you exactly where every step is coming from and make sure that you guys are getting everything right every step of the way, right? Because you can tell just from the diagram it's going to be a little bit involved, right? Those chapter 8 puzzles are due on Friday. A lot of students already turned this in because we covered them all by the end of class yesterday, right? But if you want a couple more days to look at those, think about those, then go ahead, just turn them in before the weekend. And right before I hit record today, I gave you guys your next quiz, rotational dynamics quiz. Let's have that due on Monday. So he's got a few days to do that take-home quiz. All right, so you guys good with what we're doing? All right, let's switch over to this rotational inertia lab. Ooh, right. So you guys see this pipe contraction in front of me? If I grab on the center and spin it, it's right here. Okay. Ooh, I feel some resistance to change in motion. Ooh, okay. And that resistance to change in motion, what's that called? Inertia. Ah, right. And since it's in a rotational sense, I'll call that rotational inertia. I bet there's some way I could quantify that, right? Hey, maybe if I take on like more masses here, I bet there would be like more resistance to change in motion, like more rotational inertia, right? Now it's low friction. There's a tiny bit of friction. Right? Hold on to that idea. That'll come back by the end of class today. Okay? But it's pretty free to spin. Now what's the setup here? Setup is not obviously see it right there, but playing off this for the video. I'm going to hang some lab weight on a string hanging over this pulley, which is wrapped around the center post of this pipe system, right? Which is going to cause a torque, right? There's some radial size of that central pipe crossed with the tension of the string is the force. That's R cross F. Hey, that's a torque. And I know that torque is also equal to I times alpha. And the whole question of this lab is what is I, capital I, rotational inertia, right? Okay, so that's what we're going to do. That's like the big picture process, right? R cross F equals I times alpha, because those are the two perspectives on torque. And if we can get R and F and alpha, then we can calculate I, right? I have a column here for on the table for I. We're actually going to do that in a graph. I'm going to modify this table a little bit. I'll draw it with you guys, right? Then, right. Well, how are we going to get alpha though? Well, that's related to acceleration, but that has to do with, hey, maybe falling distance and some falling time. Well, that's why you guys have stopwatches, right? So let's put it all together in a table. I will draw this table. Will you guys draw this table? I'm going to modify it a little bit. Yeah, do little changes, right? So you guys got this paper in front of you? Right. Did you guys write your name on your paper? Name? You guys write name? Right. I'm going to make a 10-column table. Can you guys divvy a paper into 10 columns? Right. Ooh, conveniently, the width of that paper is a little over 10 inches. So hardly ever use inches in this class, but it's might be a good opportunity right here, right? American paper. Right. Boom, I got 10 columns set up. So extend those all the way down. Right. So we're gonna keep a table of data on one side of the paper. Closer to the end of class, I'll have you guys make a graph on the back. I'll help you guys out with that too. Show you guys exactly how to put that graph together. Okay. All right, you guys have 10 columns just like I have. Right. Right. So playing off this table, like we normally have in this class, the top row can be variables, and the row right beneath that is the attached units. So then I can just record a bunch of numbers, and all those numbers will have that as attached units. Right. So variables and units. Right. Right. Now I'm not going to exactly copy this down. I'm going to modify it a little bit. So let's do different trials. Let's do what's the radius of that central pipe in meters. Right. Although it's only a little over a centimeter, but I want all my values in base SI units, so meters in this case. Right? What is I'm going to swap these two columns. Right? Let's do what is this falling distance also in meters? So I'll call it X, also in meters. Right? You can see I have the meter stick lined up next to it. It's not quite a meter. Right? Get that. Right? What mass am I hanging? this lab mass, right? Now this is going to be, you can think of this kind of like an independent variable. I've got a whole box of lab weights. I'm going to attach on different lab weights. All right, so what is the mass in kilograms? Right? What is the falling time, right? Oh, stopwatch. That's why you guys have stopwatches, right? It's going to take some time to fall at distance. So there's the time measured in seconds. Okay. Then acceleration, right? Some linear acceleration. Now, if you think about it, if this system starts from rest, boom, there's a kinematic value. Falls some distance, boom, there's a kinematic value. In some time, boom, there's a kinematic. Hey, there's 3 kinematic values, right? V naught is 0, x is some falling distance, t is some time, right? That means that in principle, you can calculate 2 other things. You can figure out the acceleration and also the crash speed. Right now, we're not so interested in crash speed, but in acceleration, we do care about, right? You guys see this top kinematic formula right here? This goes way back to what, like August, September this class. Starts from rest, this guy goes away. X equals 1/2 at squared. If you know the falling distance and the stopwatch time, can you calculate acceleration? So see, multiply this 2 over, it's 2x divided by t squared, 2x over t squared. You guys see that? Right. You guys seen that before. I know back in the Atwood lab, I remember was one specific application, and I'm sure it's come up a few other times too in this class. So, so far I have measured values, but here, whoops. Almost forgot. All right. I'm gonna slip in another column right here. We're gonna make this measure time, but we're gonna do a few measurements and take an average. So let's do a separate column for t average, right? Also in seconds, right? Now we're ready for acceleration in meters per second squared, right? But now we're moving on from measurements to calculations. And the acceleration, the linear acceleration of this falling lab weight, I just showed you guys how to get it. It's equal to, and this is the calculation, 2 times the falling distance divided by the falling time squared. Okay, it comes from kinematic days. Okay. Well, if you know the linear acceleration of this lab weight falling down, and that's tied to the string, which was tied around the central post, which is causing this to speed up spinning. Hey, speed up spinning. That's called angular acceleration. The linear acceleration of this lab weight and the angular acceleration of this pipe system are related by this right here. Right, you guys remember turntable physics? Right. So what's linear acceleration, angular acceleration? They're related by the radial size. If I want alpha, all I have to do is take a and divide by r. And that's exactly how we're going to get the angular acceleration alpha in radians per second squared of the whole pipe system. We're just going to say equals a divided by r. Boom, just like that. Right, this a divided by this r. Okay. Then what else do I want? Let's do tension force. So F sub t measured in newtons. Right. Now this we're going to calculate. Now you might be thinking, well, if I hang on a lab weight, isn't this tension, which is providing the torque? That's why I want the tension in the string. Right? Isn't the tension just equal to the weight? And that's almost true, but not quite. If it's hanging at rest or falling at constant speed, then that would be true, right? The tension would just be equal to the weight. Right? But it's actually accelerating down. So let's go back and recap elevator physics, because we need some elevator physics going on. Right? So I've got a separate piece of paper. I'm just reminding you guys something in your notes from a few months ago. Right? You guys remember there's a guy in an elevator, and there's a cable that's let the elevator move up and down, right? Or if he's standing on a scale, he's getting the normal force reading on the scale. It's the same math lesson I'm about to do, right? Let's say he's accelerating down, just like the lab weight's about to in this lab. Right? What would the free body diagram look like? Well, let's say he has a weight pulling down. I'll call it mg. Right? And there's a tension in the string or this elevator cable pulling up, but I'm not going to make that as much. So F sub t like that. So there's an imbalance. So there's a net force downward. So he's accelerating downward. Newton's second law of motion. Net force equals mass times acceleration. Well, net force is the difference of these 2 forces. If I call down the positive direction, then weight's pulling down. I'll do minus the tension force upward, because that's resisting that motion, equals mass times acceleration. Right? And if I make a connection to the lab that we're about to do, we'll see, well, you'll have mass at this point. We're going to assume a value for gravity free fall. Let's call it like 9.8 meters per second squared. At this point in the lab, you would have calculated the linear acceleration. So we're trying to figure out what is the tension force. If I rearrange that, I'm getting tension force equals, that's mg minus ma. If you like, you could factor out the mass and get this right here. The tension force in the string is m times G minus A. You guys remember this from a while back? Right. And then let's check this with some boundary conditions. If there's zero acceleration, the tension is just mg the wave. And the other extreme is if he's in pure free fall, then G minus G is 0. Oh, that would correspond to like cutting that cable. There's zero tension if he's in pure free fall. That would go hand in hand. Right. And then for our lab, it's going to be closer to mg, but a little bit short of that. Right. So what we're going to do. Right, so that what I'm trying to get at is how we're going to calculate this tension. Say equals m times G minus A. Right. We're going to use G equals 9.8 meters per second squared. Maybe we should have made it a column. I don't know, but let's put it off the side. Right. And then finally, torque is going to be in Newton meters, and that's just R cross F. R cross F. So that radial size of the central pipe crossed with that tension force is going to give you the turning moment called the torque, right? R F torque. Okay. Well, in my pre-printed table, I also have a column for I, but let's not do a table version of that. I want to get that from a graph, but you guys will see that. Okay, good so far? All right. Let me make a bunch of rows. I'm going to make 5 rows. So 1, 2, 3, 4, 5. Right. Make these boxes kind of big because each cell will have one number in it, except for the measured time column. I'm going to do like 3 values and then take an average. Right. So let's go trial 1, 2, 3, 4, 5, and then each of these trials will have like 3 sub trials with the time. Right. Now to save a little bit of time, I'm just going to go with 3 stopwatch values. Right. You guys got stopwatches? So I'm about to pull some volunteers and then have you guys keep track of how much time. We're going to make believe we did 3 separate trials, right? But we'll just do 3 times. Right? So cut a little corner there, but that'll be right. Right, you guys go with the premise, what we're doing? Right. So ultimate question is, what's the rotational inertia of this whole pipe system? Right. And actually, you know what? I can think of 2 different ways to get it. There's this whole empirical process we're going to do. And then we'll have torque and alpha, and we can set those two to each other. I know that torque is R cross F, but torque is also I times alpha. And then the ultimate question is, what is that rotational inertia? Okay. Before we get going on this particular procedure, I'm going to make a prediction from a completely different point of view. And that is to use this rotational inertia table. And then by the end of class, I'll come back and we'll see how close this is. Okay? Because that pipe system rotating, that sure does look a lot like this right here, doesn't it? Right? Or if you like, maybe some version of this and times 2, right? Same thing, right? I could play off either one of these. Right? Or if you like, there are a couple of stoppers on the end, like these bobs. So maybe I could add in a little bit of this too, right? And I put all those individual pieces on a scale before school started today, right? I got these bobs on the end were about 9 grams each. Each of these individual arms, so I got an arm here that pops into a T-piece in the middle, another arm pops in on the other side. Right? Each of those individual arms is this many grams and has this radial size, right? So I can put that all together. Now, this I'm just going to do on a calculator screen. I'm not going to write this down. Right? But I'm going to add all the bits together. Let me use these values with, well, I'm going to do this times 2 and then also add those. So let's do it. Let's do, playing off this, 1/3 times the mass of an arm was this many grams. No, I should convert that to kilograms. I should. So let's go times 0.1397 kilograms times L squared, which is the radial size, 62 centimeters. I should call that 0.62 meters and square that. Right. Now that's one arm, but there's obviously the other arm, so I'll say times 2. Right. Then plus, and I do have those bobs on the end, so I'll just do mr squared for each one of those. So I got the mass of each one was 9.4 grams. So that's, well, there's probably like 9.4 on 1,000 to turn to kilograms times its radial distance, which is the same thing as those 0.62 meters, right? Square that, right? Then also times 2, because there's 2 of them, right? There's one on one side, one on the other side. So that's that times 2, right? Now that's most of what's going on. I am kind of ignoring the central pipe here, although that's such a small radius compared to everything else, saying, maybe if I kind of toss that out. I bet the number on my screen is going to be pretty dang close to the rotational inertia of this pipe system, but maybe a small underestimate. Right, let's see what number I'm getting. I'm getting this number right here. So I'm going to say I equals rotational inertia 0.043. Guys, what's the unit for rotational inertia? How do you measure mass? Kilogram. How do you measure radius? Meters. In a squared, kilogram meter squared. Right. I'm going to make a prediction right here that by the end of class, after we go through this whole table and get the answer like empirically and calculation and graph, blah, blah, right, that the answer to rotational inertia is going to be pretty close to this number, but maybe a little bit bigger than this number, because I think this is a little bit of an underestimate. Okay, all right, you guys ready? Let's try it out. All right, got. All right, here's a table. All right, so I'm gonna put this aside and I'm gonna pull this out by the end of class. All right, you guys got stopwatches ready? All right, so who's volunteering for stopwatch? Who's volunteering? All right, let's go. Yeah, Tucker and how about Zane and Andres? All right, Tucker, Zane, and Andres. Okay, guys ready? Okay, so come over here. Let me get my visual set up for the camera. Okay. I should here while you guys are getting your stopwatches set. Okay, I should get these first two values right here. What's the radius of the central pipe? So I got a ruler right here. Let's check it out. Now the diameter is shown as 2.2 centimeters, which means the radius is 1.1 centimeters, which is called 0.011 meters. Right? Now that'll be controlled. That's the same all the way down. Okay? The falling distance, this falling distance, oh, I got a meter stick set up right here. That's going to be, let's call it 70 centimeters. You guys see it's going to fall 70 centimeters? So that's called 0.70 meters. That'll also be controlled. That's going to be the same all the way down. Okay. My first lab weight, I'm going to pull the 200 grams. I found a good starting value. That's called 0.20 kilograms. Okay. All right. And now it's ready for stopwatch time. All right, guys, ready with the stopwatches? Stopwatches? You guys know how to use them? Okay, so, okay. Right, here we go. Gonna wind it up. Gonna throw on the 200-gram lab mass right here. It's about to fall 70 centimeters. All right. All right, ready? And go. All right, so this first one takes a long time. So it is accelerating, just really slow. It's gonna take a while. Right. You can stop the stopwatch when it's the floor, but that's not gonna be for a while. Okay. It is speeding up spinning. All right. And stop. Oh, hey guys, it's still rotating, even though it's not being pulled anymore. Why is it still rotating? Yeah, okay, momentum is a good answer. Yeah, right. And it has momentum because it has inertia. Ooh, in a rotational sense, rotational inertia. Yeah. Right. No, it did stop by now because there is a little bit of friction. Right, so Tucker, what'd you get? 30.84. Right, Zane. 31.00. Andres. 30.81. All right. Okay, so let's make believe those are three separate trials, and let's take an average. So 30.84 plus 31 plus 30.81. Collectively divide by 3. I'm getting an average time of 30.88 seconds. Remember, the units are embedded in the columns. So here we go. Right. So now I'm going to add a bit of mass to this. Let's add on 100 grams. So I'll cause 0.30 kilograms. Okay. And we'll rerun. Oh, I have to rewind this. Okay. So rewind. All right. Throw on 100 grams here to bring this up to 300 grams. All right, you guys got the stopwatches ready? All right, ready? And go. So I think it's accelerating a little bit faster than before, I think. All right, ready? Stop. Tucker, what'd you get? 20.63. All right, Zane. 21.3. Andres. 21.19. All right, let's get an average. All right, 20.63, 21.3, 21.19. I'll divide by 3. I'm getting 21.04. Ooh, yeah, that was a bit faster, right? It's a smaller time. All right, so tag on a bit more mass, more weight. Let's bring up to 400 grams right there. So I'm gonna rewind this. Okay. And then okay, so now I have 400 grams ready to go. All right, bring us up to 70 centimeters. All right, guys, ready with the stopwatches? And go. And stop. 17.12. And Zane. 17.28. Andres. 17.1. All right, check it out. 17.12. 17.28. 17. And 17.17. Okay. All right, let's bring this up to half a kilogram. Rewind, rewind. Yeah, that's it.
Oh yeah.
Rewind time.
Oh yeah.
Rewind time.
Oh yeah.
500 grams. Get ready? And
Yeah.
go. What'd you get, Tucker? 14.46. 14.46. Zane. 14.38. Andres. 14.16. All right. Yeah. 14.46. 14.38. 14.16. I'm getting 14.33 seconds average. Okay, one more. I'm going to tag on another 200 grams to bring this up to 0.70 kilogram. So.
They don't like how it spins. So fun that it spins. Yeah.
It's rewind time.
It's rewind time.
All right, 700 grams. All right, you guys ready? And go.
Going faster. After so slow.
And stop. All right, Tucker.
I got 11.53.
11.53. Zane. 11.75. Andres. 11.62. Hello. 11.53. 11.75. 11.62. Divided by 3. That is
17.
11. Oh, did I type that right? Okay. 11.63. There you go. All right. So now we're moving on to these last columns, and in the setup I was telling you how to calculate those, right? And of course, how it's going to ultimately lead to answer the question, what is the rotational inertia, right? So linear acceleration. So that comes from kinematic motion. It's 2 times the fall distance over the fall time squared, starting from rest, which is exactly what we got. So 2 times 0.7 meters divided by 30.88 seconds, and then square that time comes out to be. Now these are going to be tiny, tiny accelerations. So the first one is 0.00147 meters per second squared. Right? I'm keeping all my numbers in base SI units. Right? You guys remember pure free fall would be like 9.8. This is 0.00 something. Okay, so thanks. All right, next one. One reason I really like this model calculator is if you're doing the same type calculation over and over, but you're just like swapping out one number, all you have to do is scroll up, scroll over, leave everything locked in place. It's the same, which is that's the same. Right, and then just swap out this number right here, 21.04. That's being squared because it's the same too. Right, 0.00316 meters per second squared. Next, scroll up, scroll over, 17. Being squared, 0.00475 meters per second squared. Next, scroll up, scroll over, 1433. 0.00682 meters per second squared. And finally, scroll up, scroll over, 1163. This is 0.01035 meters per second squared.
What, 35?
0.01035 meters per second squared. Okay. All right. Now, if you know the linear acceleration of the falling lab weight and the radial size of the string wrapped around the central pipe, then you can calculate the angular acceleration of the speeding of spinning. Right? All you do is A divided by R. We talked about that earlier. So let's take the first linear acceleration, 0.00147 meters per second squared, divide by the radial size in meters, which is 0.011. Got all tiny numbers today. Right? That's going to give us angular acceleration is 0.134 radians per second squared. Right, next one, 6, right? And then all the other bits are the same. 0.287 radians per second squared. Right, next one, 0.432 radians per second squared. Next one, 0.620 radians per second squared. And last one, 0.941 radians per second squared. That's quite a bit of precision, but I guess better too much precision than not enough. So we're all right. Okay. All right, so that was the angular acceleration. Now, what torque was causing that angular acceleration? Well, we need the force and then R cross F. So what was the force? What was the tension in the string? We talked about that earlier from elevator physics. That's M times G minus A. So let's take the lab mass. The first one was 0.2 kilograms, and then times, G minus A. So we're going to use 9.8 meters per second squared for G. Subtract, remember, that's a tiny linear acceleration, 0.00147, right? And I'm getting, I'm getting around this to 2 decimal places, so 1.96 newtons, right? You might notice for this particular lab, even if you forgot to subtract the acceleration from gravity, the answer wouldn't really change a whole lot, right? Let's go all the way down here. Next one. So now we got 0.3 kilograms. Gotta put in here 0.0316. Right? This is like 2.94 newtons of tension. Next one, got 0.4 kilograms. 9.8 minus 475. Right. This is 3.92 newtons of tension. Next one, I got 0.5 kilograms. 9.8 minus 0.0682. This is 4.90 newtons tension. And finally, got 0.7 kilograms. It's accelerating 0.035. It's like 6.8 0.85 newtons of tension. Right. To show you guys, what if you had forgotten to like subtract A? What is M times G? So here's M times G. You would have gotten 6.86 newtons instead of 6.85 newtons. Okay, wouldn't have made a huge difference. Just a side thought. Right? Finally, torque. Torque. Right. Well, torque is R cross F. We have R. We have F. There's R and F. Right. R cross F. Right. And since we're talking about a cross product, we want the perpendicular components. Now, quite conveniently for the setup, R and F will always be perpendicular. Okay? What you guys see this before? Whenever you wind a string around a turntable, in this case around the central pipe, as long as you're pulling the string horizontally, you can pull it at any direction, and the radius will always be perpendicular to however you pull it, right? Or whenever you pull around a pipe like that. Okay? So R cross F, all we have to do is multiply these two numbers. That's what I'm saying. Okay? So let's take radius of that many meters. Okay, which is locked in place, right? 0.011 meters. That's controlled times this tension force, 1.96 newtons. Right? I'm getting 0.022 Newton meters of torque. Next one. Okay. Scroll up, scroll over, pop in this many newtons of tension. I'm getting 0.032 Newton meters of torque. Next, 3.92. 0.043 Newton meters of torque. Next, 0.054 Newton meters torque. And finally, 0.075 Newton meters torque. Okay. Right. Good so far. Good so far. Right, okay. Maybe I should put a title on this. Rotational Inertia Lab. There you go. I got a lab title. Rotational Inertia Lab. All right, guys, ready to make a graph? Graph time. Right. Now, why are we making a graph? What are we looking for on the graph? Right. Well, it's these expressions up here. Maybe we should copy paste that right here. Torque is R cross F. That's what we just did. But torque is also equal to I times alpha. Right? Torque is I times alpha. The whole question we're trying to answer with this lab is what is rotational inertia? That's that I value. Right? And we have 5 different torque values. Bam, 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 bam. And we have 5 different angular acceleration values. Bam, 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 bam. They correspond to. Right. Oh, this looks a lot like y equals mx. So that's exactly what kind of graph we're going to make. Okay, graph time. Let's make a couple of axes. On the vertical axis, I'm going to put torque in Newton meters. On the horizontal axis, I'm going to put angular acceleration in radians per second squared. So I have torque versus angular acceleration. Okay. Right. Everybody have that? You guys drew a couple of axes. You guys wrote that title, tau versus alpha, torque versus angular acceleration. You have each of the axes labeled with units, right? So we got torque in Newton meters and angular acceleration in radians per second squared. Right? Now it's time to scale these axes. Well, my largest torque was 0.075 Newton meters. So let's do that right here. Go, bam, bam, bam. Let's go 0, 0.025, 0.050, 0.075. Okay. And then angular acceleration, see the largest value was just a little bit less than 1 radian per second squared. So should scale it like that, right? How about 2, 4, 6, 8, 10? Let's go 0, 0.2, 0.4, 0.6, 0.8, and 1.0 radian per second squared. Yeah, that's right. So we'll be able to put all our data on that space right there, right? And I'm predicting that all 5 points are going to line up in a straight line. Torque equals I times alpha, and we'll get the slope of the line, which will be the answer to the question. Okay, what is rotational inertia? Yeah, let's do that. Let's plot some coordinates. So I got alpha and torque is like my XY values. So 0.134 radians per second, 0.134 radians per second squared, and 0.022 meters of torque. That's like, bam, right there, bam. Here's the first point. Next point, next coordinate, 0.287, and 0.032, 37, 032, that's right up there. Bam. Next one. Right, third coordinate, 0.432, 0.432, 0.043, 432, 0.043. Bam. Fourth point, 0.62, and then 0.054, 0.054. Bam. And last point, 0.94 radian per second squared, and then 0.075. 94 up there, 75 there. Bam. Okay. Hey, look at those 5 points. They pretty well line up on a straight line. Let's do a line best fit right there. Zip. All right, look at that. Look at that. Straight line. Oh, but you know what? Guys, if I extrapolate backwards to the axis, guys, does that line go through the origin? It does not. It misses the origin. It definitely misses the origin. There's definitely like a y-intercept here. Maybe I should say a tau intercept. Ooh, like torque. Okay. What does that mean? Why is there an intercept here? What does that mean physically? How about this? Give you guys a hint here. Right. Oh, at that point, see, there would be 0 angular acceleration, even though there is already a torque provided. Hey, could that be like if I take a relatively small lab weight? Like, what if I took this like little tiny 50-gram guy and attached it? Right. Let me try that right here. While you guys are thinking about that. It's rewind time.
It's rewind time.
Rewind time. Okay. And I'm gonna spec just a little 50-grammer on this guy. Okay. What's gonna happen? Ooh, it doesn't actually rotate. Why doesn't it rotate? Because there's what?
Small.
A small amount of friction. This right here is the frictional torque that you have to overcome before it'll rotate at all. Now, once you overcome that frictional torque, then it looks like a constant slope line, which is like a constant rotational inertia. Right? I have torque equals rotational inertia times angular acceleration. Right? Plus frictional torque, I guess to say, right? Plus frictional torque. Here's the frictional torque. Y equals mx plus b. So the slope of this line is the answer to the question, what's the rotational inertia? Let's do rise over run. If I pick the first point and the fifth point, but it's pretty well line on the line. I think that'll work, right? So could rotational inertia be the change in torque over the change in angular acceleration? Okay. So here, I'll play off these two right here. So the change in torque is, here, I'll go ahead and spell this out. Okay. That's 0.075 minus 0.022. That's Newton meters. And then the change in angular acceleration, the corresponding change is 0.941 minus 0.134. That's radians per second squared. Okay, so put it all together here. What is 0.075 minus 0.022? Group together in parentheses. Divide by open parenthesis. 941 minus 0.134, right? Make sure you can correctly type that in the calculator, right? Now, before I hit enter, I remember before I started spinning that thing at all, we made a prediction. I was looking at that rotational inertia table. You guys remember this table right here? Actually, I guess the left side of this table, right? And I was adding up all the little bits. And I was saying, I think, based on that table, the rotational inertia should be at least this value. Should be pretty close to this value, but this might be kind of an underestimate or on the lower end, right? So as soon as I hit enter to get the slope of this line, we'll get the actual answer, I equals something. Right? And moment of truth, I wonder how close it is to this. See if it's a little bit bigger than this. You guys ready? And pow! Look at there. 0.066 kilogram meter squared. Right? I was predicting at least 0.043. I'm getting 0.066. Yeah, that is definitely the same order of magnitude. And also, it's about what I was thinking too, right? So it should be a little bit bigger than what I added up. Because when I added up, I was ignoring the central pipe itself. Right, might be one reason it's underestimate. Guys always wobble a little bit, so maybe that central axis has a bit more of a radius than its own radius. Right? All right, so there you go. There's the actual answer to the lab. Right, you guys go with that? All right, so double check that your name is on your paper. Your name's on your paper, right? All right, toss that in the grade tray. All right, and that is a wrap on today.